Hello friends, I've cleared the OCI Generative AI Professional certification. This podcast helps you quickly grasp key concepts and crack the exam. Listen while driving, walking, or before sleeping. All the best.
All right, let's get right into it today. We are doing something a little different, a bit more targeted for this deep dive.
Yeah, a hard launch today.
Exactly. We're diving straight into the Oracle Cloud Infrastructure Generative AI Professional 2025 certification.
Right, the 1Z0-1127-25 exam.
That's the one.
Yeah.
And the goal today is pure exam preparation. No fluff, just the concepts, the questions, and those little syllabus gotchas you need to watch out for.
Because we want you seeing that green tick on your results screen. That is the mission.
Absolutely. So we are decoding the whole thing, from the base architecture all the way up to RAG and agent lifecycles.
It is a lot of ground to cover.
It is. So grab your notebook, maybe, open a terminal window if that helps you think, and let's get to work. First up, we really need to lay the foundation, the hardware, the clusters.
Right. Because in OCI Generative AI, everything runs on what we call dedicated AI clusters.
Okay.
And for the exam, you have to understand these aren't just your standard generic virtual machines. We are talking about highly specialized, isolated environments, specific GPU shapes.
Like the A100s and H100s.
Exactly. The BM.GPU.A100 or the H100. But the absolute most critical distinction you have to make right away is between the two types of clusters.
Right. There are two distinct flavors here. What are we looking at?
You've got fine-tuning clusters, and you have hosting clusters. And I guarantee the exam loves to test if you know exactly which one does what.
So let's break that down for everyone listening. What is the fine-tuning cluster actually doing?
Think of the fine-tuning cluster as, well, like a temporary workshop. It's an environment that is strictly for training custom models.
Only training.
Only training. So maybe you're using LoRA or some other PEFT method, which we will definitely get into later, to train on your own specific data set.
Okay, so you spin it up, you do the heavy lifting of training the model, and then...
And then you're done. You shut it down. It is temporary by design.
Got it. So if the fine-tuning cluster is the temporary workshop, then the hosting cluster is what, the showroom?
Yeah, in a way. But a showroom that works incredibly hard, hosting clusters are persistent environments.
Like Aeon.
Right. This is where you deploy your models for inference. So when you create a model endpoint to actually serve API calls, for a chat application or text generation, that lives on a hosting cluster.
Okay, so here's a classic exam scenario. If a question describes a company that needs to handle a, let's say, high workload inference task, and it asks which cluster type you should provision.
You choose hosting every single time. Inference equals hosting. Training equals fine-tuning. Don't let them trick you.
Simple enough.
Yeah.
But then we get into the sizing, which is where I think people get a little turned around with this concept of Unix.
Oh, the unit requirement, yes. This trips people up constantly because they try to overcomplicate the math. They try to calculate the cluster units based on the size of their data set or how many files they want to process.
Which is completely wrong.
Completely wrong. In OCI, the cluster unit size is determined strictly by the base model you select. Nothing else.
So it's essentially just a fixed cost based on the model.
Exactly. It is a predefined value set by Oracle. For example, and this is a highly specific fact from the source material that you should absolutely memorize.
Let's hear it.
If you are using the cohere.command-r-08-2024 model,
the August 2024 Command R model.
Right. That specific model requires a fixed cluster size of 8 units.
Just flat out 8 units.
Yes. You don't calculate that. You don't sit there and think, well, I only have a small text file. Maybe I can just provision 4 units. No. The hardware requirement for that model is 8.
Okay, so that's hard rule. Command R 08-2024 equals 8 units. Now, speaking of hard numbers and rules, let's talk about the limit that involves a little bit of math, the 50 endpoint limit.
The math question. This is such a classic certification pattern.
Yeah.
So here's the rule you must burn into your brain before you walk into the testing center. A single hosting dedicated AI cluster supports a maximum of 50 endpoint.
50 endpoints. And an endpoint is just a deployed instance of a model that you can hit with an API call, right?
Correct. Now, here's the scenario they're going to throw at you. The exam might give you a use case where a customer has a massive global application and their engineering team determines they need 60 endpoints to handle the concurrent traffic.
Okay.
The question will ask, how many dedicated AI clusters do you need to provision to support this?
So we just do the basic math. If I provision one cluster, I max out at 50.
Right. And 50 is less than 60, so one cluster is obviously insufficient.
Which means I need a second cluster.
Exactly. 2 clusters gives you a total capacity of 100 endpoints. Since 100 is greater than the 60 you need, 2 clusters is the correct answer. The underlying logic is just a ceiling function.
Like ceiling of 60 divided by 50.
Right. 60 over 50 is 1.2. Round up to the nearest whole number, you get 2.
Now, let me ask a clarifying question on that. Does the size of the underlying model change that math at all?
Right.
Like if I'm running a massive 405 billion parameter model versus a tiny little embedding model, does that 50 limit go up or down?
No, it does not. And that's exactly the nuance they test for. The limit applies per cluster regardless of the model size. Huge model, small model, doesn't matter. The hard cap is 50 endpoints per cluster.
Okay, what about this feature I hear about called stack serving, where you can host multiple versions of a model?
Stack serving is a great feature. It allows you to host multiple fine-tuned versions, say you have different T-few fine-tunes for different departments, on the same cluster, assuming they share the exact same base model.
Which saves a ton on hardware costs.
It does. However, and this is the crucial part, the hard cap of 50 endpoints still applies to that cluster.
Oh, I see.
Yeah, you cannot use stack serving as a loophole to get 51 endpoints on a single cluster. The limit is absolute.
Crystal clear. 50 is the magic number. Let's pivot slightly and talk about billing, because obviously the exam covers how OCI charges for all this, specifically on-demand billing.
Right. On-demand billing is based on transaction volume, but the word transaction has a very specific definition in this context. It is based entirely on total character length.
Total character length, not tokens.
Characters. And specifically, it is the prompt characters plus the response characters. The formula is literally 1 transaction equals 1 character.
Okay, so let's run a quick scenario. I send the model a prompt that is exactly 200 characters long. The model thinks about it and writes me a nice little summary that is 500 characters long. What am I billed for?
You take your 200 character input, you add the 500 character output, and you get 700. You are billed for 700 transactions.
It's purely additive, just input plus output.
Purely additive. Do not let the exam trick you into selecting an answer that says you're only billed for the generated text or only the prompt. It is always both combined.
Okay, that makes sense. Let's move on from the hardware and the billing into the actual brain of the operation. Part 2 of our deep dive. Configuring the model. We are talking about parameters and decoding strategies.
The knobs of generation.
Exactly. These are the dials we turn to change how the AI behaves, how it sounds. And the most famous dial, without a doubt, is temperature.
Everyone knows temperature, or at least they think they do.
The standard advice is high temperature is creative, low temperature is robotic, right?
It's the high-level view, yeah. But for the exam, you need to be technically precise. A high temperature, let's say 0.9, increases randomness. It makes the model's selection of the next token much less predictable.
Which is great if you're writing a sci-fi novel.
Sure, but in an enterprise setting, it significantly increases the risk of hallucination.
Hallucination being when the model just states false information with complete confidence.
Correct. Now, on the flip side, a low temperature, like setting it all the way down to 0.0, makes the model deterministic. It becomes highly factual, highly grounded. It vastly reduces the risk of hallucination.
What is actually happening mathematically under the hood when I change that number?
Mechanically, the temperature parameter scales the logits. The logits are the raw prediction scores for every possible next word. It scales those logits right before they're passed into the softmax function.
Okay, so if the temperature is greater than 1,
if it's greater than 1, it flattens the probability distribution. It makes all the possible words look equally likely. It introduces chaos.
And if it's less than 1?
It sharpens the distribution. It makes the already probable words look even more probable and squashes the unlikely words.
So a temperature of 0.0 is basically telling the model, just pick the absolute most statistically likely word every single time, no exceptions.
Precisely. It removes the randomness entirely. Now, working right alongside temperature is top. You'll also see it called nucleus sampling.
How does top differ from top? Because they sound very similar.
They do, but they operate differently. Top kicks a fixed, hard-coded number of words to consider, like only look at the top 5 words. Top is much smarter.
How so?
It dynamically selects tokens until a cumulative probability threshold is reached. So let's say your top is 0.9. If the single most likely next word has a 90% probability on its own, top stops right there. It only considers that one word. But if the top 10 words each have a 9% probability, it will include all 10 of them in the pool to reach that 90% threshold. It's dynamic based on the confidence of the model at that specific step.
So how do temperature and top interact? What if I set a high temperature to be creative, but a really low top?
Lowering the top constrains the model. Even if your temperature is cranked up, telling the model to be wild and random, a low top puts a leash on it. It restricts the pool of words the temperature can choose from to only the most sensible, high probability ones.
So it's a way to achieve safe creativity.
Exactly. Now, what if the model starts acting weird and just repeats itself? Like the cat sat on the mat, on the mat, on the mat.
I've seen that happen. How do we fix it?
That is where your penalties come in. You have the frequency penalty and the presence penalty.
What's the core difference between the two?
The frequency penalty penalizes a token based on how many times it has already appeared in the text.
So it counts.
It counts. If a word has appeared 5 times, it gets penalized 5 times harder than a word that appeared once. It aggressively discourages those repetitive loops. If you have a low or 0 frequency penalty, you are more likely to see that loop behavior.
And the presence penalty?
Presence penalty doesn't count. It is a strict binary check. Has this word appeared in the text at all? Yes or no?
So if it appeared once, it gets penalized. If it appeared 20 times, it gets the exact same penalty.
Correct. It just checks for presence. The goal of the presence penalty is to encourage the model to transition to new topics rather than dwelling on the exact same concepts over and over.
Got it. Frequency counts the repetitions. Presence just checks the binary existence. That's a great way to remember it. Now let's talk about a decoding strategy that sounds almost selfish. Greedy decoding.
Greedy decoding is the absolute simplest generation strategy. At every single step, the model looks at the list of possible next words and simply picks the one with the highest probability.
That actually sounds like a logical thing to do.
It sounds logical, and it is deterministic, but it has a major flaw. It doesn't plan ahead. It is completely short-sighted.
Because it's only looking at the very next step.
Right. It can lead to repetitive or even incoherent text because it might pick a word that makes perfect sense right now, but grammatically backs the sentence into a dead end 3 words later. It produces very flat, robotic, predictable text.
Okay, let's move to the next parameter, the seed. And I love discussing this one because of the lottery ticket analogy from the source material.
Yes, the seed parameter. It is simply an arbitrary integer used to initialize the random number generator inside the model.
I think there is a massive misconception among users that a lower seed number is somehow higher quality or more factual.
It is a huge misconception. And listeners, please note this for the exam. Seed 40 is not more factual than seed 500. Seed 1 is not better than seed 9,000. They are mathematically equivalent in terms of output quality. They're just different starting points for the mathematical randomness.
So if they don't change the quality, why do we even use them?
Reproducibility. If you do not provide a seed, the model picks a random one every time you call it, and you get diversity. You get a different answer every time.
Which is usually what you want in a chat app.
Right. But if you are a developer and you are writing automated tests for your code, you need consistency. If your test asks the model to tell a joke using seed 123, you want it to return the exact same joke, word for word, every single time that test runs.
So it basically freezes the chaos for debugging.
Exactly. It makes the random process repeatable.
Moving on to prompting techniques. We hear the term prompt engineering everywhere, but the syllabus explicitly distinguishes between soft prompting and hard prompting.
This is a fascinating shift in how we interact with these systems. Hard prompting is what you and I do every day. We type explicit text instructions, explain this like a teacher, or summarize this document in 3 bullet points.
It's human language.
Right. Soft prompting is completely different. Soft prompts are for the machine. These are learned numeric vectors, hidden tokens that you feed directly into the model. You don't type them out as English words.
So you train a series of numbers that guide the model's behavior.
Yes. It is like injecting a specific mood or a specialized skill directly into the model's latent space without ever using natural language.
That sounds incredibly sci-fi. We are definitely going to circle back to the implications of that in the outro. But one last thing on configuration, multimodal parsing.
Right. This is about handling complex documents that aren't just plain text. When you have PDFs with charts, graphs, and images embedded in them.
There is a very specific note in our source material regarding diffusion models and how they handle text.
Yes. Diffusion models, which are typically what you use for image generation, notoriously struggle with rendering text accurately.
Why is that?
Because of the nature of the data. Text is categorical. A letter is either a B or a C. There is no halfway point. It is discrete data. Images, however, are continuous data. Pixels gently blending into other pixels.
Oh, that makes sense.
Diffusion works by gradually removing continuous noise to reveal an image. It is fantastic at continuous gradients, but it has a very hard time resolving the sharp, discrete boundaries required to make legible text characters. That is exactly why you often see AI-generated storefront signs with completely alien gibberish written on them.
That explains so much about those weird AI images. All right, let's shift gears to part 3. This is the heavy lifting of the syllabus, fine-tuning and customization.
Fine-tuning is the next logical step when your prompt engineering just isn't cutting it anymore. Maybe your data format is too complex for instructions, or the context window, the amount of text the model can remember at once, is simply too small to fit all your rules and examples in.
So what is the actual goal when we decide to fine-tune?
You are fundamentally adapting the model's weights to specific task patterns. You want to improve its efficiency and its relevance for your specific use case.
Yeah.
And we evaluate how well we did that using 2 key metrics: accuracy and loss.
Let's define those clearly for the exam.
Accuracy is very straightforward. It is the proportion of correct predictions. Did the model's output match your target output? Higher is better.
And loss.
Loss is a bit more nuanced. Loss measures the penalty for a bad prediction. It measures how wrong the prediction is compared to the ground truth. It quantifies the discrepancy. So obviously, you want your accuracy to be high and your loss to be as low as possible.
Okay. Now, we have a few different methods for fine-tuning. It isn't just a one-size-fits-all button you press.
Far from it. You have vanilla or full fine-tuning. This is the traditional method where you update every single parameter in the entire model.
Which sounds incredibly computationally expensive.
It is massively expensive. It takes a ton of time and a ton of GPU memory. That's why we have more efficient methods now.
Right, like TFEW.
Yes, TFEW stands for task-focused. It selectively updates only a specific fraction of the model's weights that are mathematically relevant to the task you are training it on. It ignores the rest.
But the really big one, the one everyone in the industry talks about, is PEFT and LoRA.
PEFT stands for Parameter Efficient Fine-Tuning. It's an umbrella term. And LoRA, low-rank adaptation, is a specific type of PEFT.
How does LoRA work compared to full fine-tuning?
Instead of changing the massive base model, LoRA inserts tiny, small adapter layers into the architecture, and it only trains those tiny adapters. The entire base model stays completely frozen.
So it's like putting a specialized filter over the lens instead of rebuilding the whole camera.
That's a great analogy. It is huge for the industry because it is highly efficient, runs much faster, and has a drastically lower memory footprint. You can train a LoRA on consumer hardware sometimes.
Now, there is a specific historical date mentioned in our source regarding the cohere.command-r-08-2024 model.
Yes, a piece of trivia you need to know. Full fine-tuning capabilities for that specific August 2024 Command-R model became available on OCI around October 3rd, 2024.
October 3rd, 2024.
Right. Before that date, you might have been restricted to only using TFEW or LoRA for that model, so just keep that date in your back pocket.
Marked it down. Now, getting back to the math, because there's another formula here. Calculating training steps. This feels like a guaranteed exam question.
Oh, it absolutely is. The exam will give you a scenario and ask you to calculate the total training steps for a fine-tuning job. The formula you need is total training steps equals total training epochs multiplied by the size of the training data set, and then that result is divided by the training batch size.
Let's unpack the logic of that so people don't just have to memorize abstract variables.
Think about the process. One epoch means the model has seen your entire data set from start to finish one time. So if your data set has 1,000 records and you configure the job to run for 3 epochs, the model is going to process 3,000 records in total.
Right. Epochs times data set size. 3 times 1,000.
But the model does not process one single record at a time. That would be too slow. It reads them in chunks, called batches. So a step is simply the act of processing one batch.
Right.
So you take that total number of records to be processed, which we established was 3,000, and you divide it by your batch size. If your batch size is set to 10, then 3,000 divided by 10 equals 300 steps.
That makes perfect sense when you break it down. Total items seen divided by how many items you pull in at once.
Exactly. Don't let the formal notation in the syllabus scare you. It is just basic grouping.
All right, moving right along to part 4. The developer experience. We are diving into the Python SDK and the actual code. The source explicitly notes that this usage section makes up 40% of the exam.
That is a massive chunk of your score. And the strategy for this section is very specific. The exam is going to show you a block of Python code and essentially ask, what is this script trying to do?
So we really need to recognize the specific client methods. Let's run through the greatest hits, starting with authentication.
It almost always starts with oc.config.from_file. That method loads your OCI credentials. Then you use that config to initialize the generative AI inference client. If you are looking at a code snippet and you don't see that client initialization, none of the inference calls are going to work.
Good tip. Next one, embeddings.
You'll be looking for a call to generative AI inference client.embed_text. The key parameter to watch for here is inputs.
Plural.
Yes, plural. Note that it accepts a list of strings, not just one string. You can send a batch of text to be embedded all at once. The current limit is up to 96 strings per batch call.
96 strings per batch. Excellent detail. What about standard chat generation?
The object to look for there is chat details. Inside that object, you want to look at the serving_mode parameter. Usually for a standard call, it will be set to on-demand along with a model_id. That tells you the code is hitting a standard pre-trained model on the shared infrastructure, not a dedicated cluster endpoint, unless it specifically references an endpoint ID.
And what if the code is kicking off a fine-tuning job?
You will see the method create_fine_tuning_job. But the real giveaway, the thing to scan for, is the hyperparameters object. If you see LoRA hyperparameters being passed in, you know immediately without reading the rest of the code that this is a PEFT fine-tuning job using low-rank adaptation.
Okay, so once we have a fine-tuned model, we need an endpoint to actually use it.
Right, so look for the create_endpoint method. Now, remember our cluster discussion. This method will absolutely require a dedicated _a_cluster_ed parameter. You cannot just put an endpoint on thin air. It has to be attached to a hosting cluster.
And there's a specific lifecycle status note in the syllabus about endpoints.
Yes. When you create an endpoint, or if you update it, say you need to move it to a different OCI compartment, the status changes. It goes from active to updating while the change is happening, and then transitions back to active once the operation is successful.
Finally, how do we actually invoke that endpoint from outside the OCI SDK? Say, just using standard Python.
You don't even need the OCI SDK for that part. You will often see standard Python libraries used, like a basic request.post call. It just hits the endpoint URL. The key thing the exam will test is if you know to include the authorization headers with your OCI signature. Once the endpoint is up, it acts like any standard REST API.
So the takeaway there is don't just study the OCI specific libraries. Make sure you know your basic HTTP request structures in Python too.
Absolutely.
All right, we are in the home stretch now, part 5, RAG, Retrieval-Augmented Generation. This is arguably the hottest topic in the industry right now.
RAG is essential knowledge. It solves the fundamental knowledge cutoff problem of LLMs. To truly understand RAG for the exam, you first have to understand the conceptual difference between parametric and non-parametric knowledge.
Let's start with parametric.
Parametric knowledge is the model's internal brain. It's the fixed mathematical weights and the memory it learned during its massive pre-training phase. It is incredibly fast to access, but it is permanently frozen in time. If the model finished training in 2023, it has zero parametric knowledge of anything that happened in 2024 or 2025.
It's locked. So then non-parametric knowledge is what?
That is the library, the external data sources. RAG is fundamentally a non-parametric approach. It allows the model to look up fresh information from an external source, usually a vector database, dynamically at runtime.
So it doesn't have to memorize everything.
Right. It doesn't require expensive retraining just to learn new facts. If you want the model to know about a new HR policy, you don't retrain it. You just embed the new policy document and add it to the library.
Speaking of that library, we store all this embedded data in vector databases. What is the specific database Oracle pushes for this architecture?
Oracle Database 23i. It introduces a brand new, highly optimized native data type simply called vector. That is where your embedded at live.
And we generate those vector embeddings using specialized models. Cohere is the primary partner here, and we have a few specific versions we need to keep straight for the test.
Yes, you really need to memorize the dimension outputs for these models. First, you have the standard cohere.embed-english-v 3.0. That model creates vectors with 124 dimensions.
But there is a lighter version available.
Correct. The cohere.embed-english-light-v 3.0. As the name implies, it is faster to run and uses significantly less storage memory. But you must know the exact dimension count for the exam. The light model outputs vectors with exactly 384 dimensions.
384. Okay.
And if you need to process other languages and use the specific multilingual model, cohere.embed-multilingual-v3.0, that goes back up to the standard 1024 dimensions.
Okay, so the rule of thumb for the exam is the light English model equals 384 dimensions. Everything else equals 124 dimensions.
That is a very safe rule of thumb to rely on.
Now, once we have all these vectors in the database, how do we actually find the right information when a user asks a question? We use math again, specifically cosine distance.
Cosine distance is the metric used to measure the angle between two vectors in that high-dimensional space. And here's the counterintuitive part that trips people up. A cosine distance of exactly 0 means the two vectors are identical in direction.
So a distance of 0 actually means they're the exact same thing semantically.
Right. It means maximum semantic similarity. The closer the distance score is to 0, the more similar the underlying meaning of the text chunks. It is measuring the angle between them, not the spatial magnitude.
And to make this search fast across millions of vectors, we don't just scan every single row, right? We use indexing.
If you have millions of vectors, you absolutely cannot compare your search query to every single one mathematically. That brute force approach is way too slow for a real-time chat application. So we use specialized vector indexes like HNS-W, which is Hierarchical Navigable Small World, or FEIS or IVF.
What do those actually do?
They allow for what's called approximate nearest neighbor searches, or ANN. You are trading a tiny, usually imperceptible bit of mathematical accuracy for massive, massive gains in search speed.
Let's quickly walk through the 4 steps of the standard RAG pipeline.
It's a very standard sequence. Step 1 is ingestion. You load the raw data from your files. Step 2 is chunking. You split those large documents into smaller, manageable pieces of text. Step 3 is embedding. You pass those chunks through the Cohere model to turn them into vectors. And step 4 is storing. You save those vectors into your Oracle 23II database.
And then when a user finally types a question into the app,
the system embeds the user's question, retrieves the mathematically relevant chunks from the database, but before it blindly sends them to the LLM to generate an answer, there is often a critical ranking step.
Ah, a ranker.
Yes, a re-ranker evaluates the retrieved chunks against the prompt to ensure high quality and semantic relevance. It filters out the noise so the generator model only sees the best possible context.
And how do we actually prove that this whole system worked? We have specific evaluation metrics for our RAG pipelines too.
The two big ones to know are groundedness and answer relevance.
Let's distinguish those clearly.
Groundedness asks a very specific question. Is the model's generated response factually traceable back to the retrieved source documents? Did the model actually use the provided context, or did it just hallucinate an answer from its pre-training? Groundedness measures hallucination.
And answer relevance.
Answer relevance asks a different question. Did the generated response actually answer the user's original prompt? You can have a response that is perfectly grounded but completely irrelevant to the user.
Like if I ask, what is the capital of France, and the model replies, the sky is blue.
Exactly. The statement, the sky is blue, might be fully grounded in a science document you provided, but it's utterly irrelevant to your question about France. You need both metrics to be high for a successful RAG system.
Got it. Groundedness checks the source data. Relevance checks the user's question. Finally, to wrap up the syllabus, let's talk about agents and their life cycles. This is really about how we manage these knowledge bases in production.
There are some very strict dependency rules here that you will be tested on. For instance, what happens if you delete a data source?
Let's say I accidentally hit delete on an important PDF in my object storage bucket.
The agent itself keeps running just fine. It doesn't crash. It simply loses access to that specific piece of knowledge. It obviously can't answer questions based on that PDF anymore, but the agent remains active.
But what if I decide I want to delete the entire knowledge base component from OCI?
OCI won't let you just delete it if an active agent is currently attached to it. It's a safety lock. You must delete the individual data sources, and you must delete the agent itself first. Only then will the system allow you to delete the underlying knowledge base.
That makes sense. It prevents you from breaking live applications. And one quick note on privacy and compliance regarding user chats. Session data.
Yes. When a customer is chatting with your deployed agent, that conversational data is retained temporarily to maintain the session context. So the bot remembers the question you asked 5 seconds ago.
Right.
But, and this is crucial for compliance questions on the exam, that chat data is not stored permanently by Oracle, and it is strictly not used to train the foundational models.
That is a very important point for enterprise customers. And what about moderation? Does OCI check what people are saying?
Yes, moderation is applied bidirectionally. It is applied to both the user input, checking the prompt for policy violations, and it is applied to the model output, making sure it doesn't generate restricted content. It's a two-way filter.
Wow. Okay. We have covered a truly massive amount of ground today, from the rigid 8-unit cluster rules to the 384-dimension light embeddings.
We really did. We hit the architecture limits, the math behind the 50 endpoints, all the configuration knobs like temperature and top, the fine-tuning formulas, the key SDK client methods, and the entire array evaluation pipeline.
I feel like anyone taking notes is in great shape for the exam. But before we completely sign off, I want to circle back to that idea we touched on earlier, the concept of soft prompting. We talked about how hard prompting is basically us talking to the AI in English, but soft prompting is feeding it learned numeric vectors.
It is a deeply provocative thought about the future of this field. Right now, we spend so much time and energy trying to chat with these models, trying to find the exact right English words to make it do what we want.
Prompt engineering.
Right. But soft prompting suggests that the future of advanced AI interaction might not be conversation at all. It might be tuning.
That's wild.
It shifts the dynamic entirely. We might eventually stop talking to AI using language and start directly injecting it with invisible math. High-dimensional vectors that we can't even read or comprehend as humans, but that perfectly guide the machine to the exact desired output. It changes the relationship from, a colleague you converse with to a pure machine that you meticulously program.
Are we really moving toward a future where we stop conversing with AI and just start vector tuning it, where the most highly paid prompt engineers aren't creative writers, but data scientists injecting invisible mathematical instructions?
Based on the efficiency of soft prompting and PFT, that seems to be exactly the direction the high-performance enterprise tuning space is headed.
It's definitely something fascinating to mull over while you study your flashcards tonight. Well, that is it for this deep dive. I hope this helps you get that passing score. Good luck with the 1Z0-1127-25 exam.
You've got this. Take your time, read the questions carefully. Good luck.